All right. I have faith that this is actually recording. Cool. So, welcome back, everybody. So, I want to talk a little bit about Lab 5, which is already graded and returned, and about Lab 6, which you're working on now. And then we're going to switch to our last major topic for the course, which is Verilog, and which will be related to Lab 7 and your last homework. But any questions before we get into that? Questions on the homework set or on Lab 6 and so on and so forth? All right, so let me just point you to something that I posted on Canvas. Lab 6 grading guidelines. Okay, so well, let me talk about Lab 5 first, and this will tie into some of the comments on Lab 6. So so Lab 5 looked good. Okay, there was obviously some issue with the Tinkercad simulation working reliably for resetting the counter. So I asked Izad about that, and he actually assigned his students to make a counter that counts up to 7 and then rolls over instead of 10. But the original version of the lab that I got from him had rolling over at 10, and he decided that would be more involved, so he made it roll over at 7. But I wired up a circuit to do the rollover at 10. I'm not using a 7-segment display. I'm just using LEDs to show the output. But this does work, but I did observe flakiness in it before. But anyway, there's 1, there's 2, here's 3, here's 4, and then 5, 6, 7, 8, 9, and then when it gets to 10, that automatically drives the reset, goes back to 0, and then 1, 2, and so on. But when I tried this at first, I was having the issue where the simulator was hanging up when it tried to roll over from 10 back to 0. And then I changed the capacitor, and I changed it back, and I changed some other things, and now it seems to be working reliably. The fact that the simulator time was freezing or going very slowly suggests something was unstable in the circuit configuration or in the simulator's analysis of it. But as I told people, that's what you put in your lab report, as your observation. That's perfectly valid. But it is workable. In experiment 1 for Lab 5, when you were building the 555 piece of the circuit, which is just this piece over here, a lot of the pictures of waveforms that I got were this, right? And yeah, that is technically what part of the waveform looked like, and if you throw an oscilloscope on your circuit in Tinkercad, that's what you see by default. But you can actually change the settings on this oscilloscope. You can change what the time per division is, okay? So what's a division? It's one line to the next. So what I have this set to right now is half a second per division. So half second from here to here, half second to the next line, half second to the next. And in really small print down here, you see 5.00s. That means the entire display is 5 seconds. Now normally oscilloscopes are used to capture information that's changing really rapidly, usually too rapidly to see, like something changing 100 times a second. But in this case, your waveform is changing, every 1 to 2 seconds. And oscilloscope's not really the best piece of equipment, but we can make this oscilloscope work for us by saying, only show us, a half second of time from one line to the next. And if we do that, we get a waveform like this. And if we, screen capture that, let's just screen capture it and open it up for viewing, right? You can get a pretty good picture of what your signal was doing, right? So remember, it's half a second from one line to the next. So the waveform is high for half, 1, about 1.4 seconds, right? A little less than 1.5. And then it's low for a half and a little more, so about 0.75, 0.8, something like that, right? So, so you can draw a picture of this waveform and show what this signal is actually doing. And one thing to note is, you know, it's high for a lot longer than it's low. It's actually high for about twice as long as it's low, and that's worth noting, right? And then if you were to put this in your lab report, rather than just showing, you know, the waveform was low and it went high, you could do something like this, right? And you can try to do some measurements. You can take a ruler and measure this out and see how long it's high and low. And you could do something like, you know, draw a line here and a line here and some arrows and say, you know, this was 1.5 seconds. And then draw a line here and say this was 0.5 seconds. And label this observed. Tinkercad oscilloscope. And then the lab asks you to predict, you know, what the waveform should look like, and that's using those formulas, 0.693 times RA plus RB, and so on and so forth. And so if you did that, you might have something like this, you know, and this might have been, you know, 1.4 seconds and 0.7 seconds, and this was calculated. And now it makes sense, you know, when it says, you know, explain any differences. Well, you know, I thought this would be 1.4 and it was actually 1.5, and this was a little shorter than I expected. This was a little longer than I expected. Now on Tinkercad, you're not going to really notice a difference, but when you do this in an actual laboratory, you'll see the observed one is different from the calculated one. Why? Because the resistor values aren't exact, the capacitor values aren't exact, right? Because it's physical world. So you can use these tools in Tinkercad a lot of different ways, right? So oscilloscope is a good one to play around with these settings, because if you make it something like, you know, 0.1 seconds per division, you just get this, right? And usually oscilloscope means we're looking at a signal that's changing up and down over time, so changing that knob setting lets you get a better view of what's going on. I'm getting a lot of reports. So the reports look good, okay? The grades reflect that too. I'm getting some reports where you know, there's a methodology section that says, you know, find the proper parts in Tinkercad and place them on a proto board, or a procedure section which says insert one end of the resistor in hole 17J and the other end in hole 20I, right? You don't need that level of detail in your lab reports. So your lab reports are written for somebody who knows nothing about what you're doing, but understands, you know, digital logic, understands Tinkercad, right? Somebody who understands the field, but not what you're actually doing in particular for a given lab. So your procedure can be as simple as, you know, make a wiring diagram with standard symbols, okay, you know, inverters and AND gates and so on, and has these things labeled, and has pin numbers and a component ID block and so on, and label this, you know, figure 3. Your procedure might just be, I built the circuit shown in figure 3 in Tinkercad, right? That will completely explain to anybody who knows how to do digital logic and how to use Tinkercad, how to repeat what you've done up to that point. They look at this, they know they need an inverter, which is a 7404, an AND gate, which is a 7408. They hook wires between these pins, right? That's a universal language for people who are versed in digital logic. So your procedure can be, you know, build the circuit shown in figure 5A in Tinkercad, and start the simulation, right? See what it does. Make sure you label things, right? You draw a timing diagram. The person reading your lab report does not have Lab 5 sitting in front of them. They don't know that it said draw a timing diagram for the expected waveform. So if they just see a waveform, right, like this, what is that, you know? So label it, you know, observed waveform, predicted waveform, things like that. Same with timing diagrams. So for experiment 2, you're supposed to make a timing diagram. 555 pin 3 is doing this kind of thing, right? And that's part of your system, but you know, there's a lot more to your circuit than just the 555. There were 4 outputs, QA, QB, QC, QD. There was also a reset input, right? Show what those are, and make sure that you label each of these things. Right, QA, QB, QC. Timing diagrams, we don't necessarily put in, you know, what the time is from here to here. They're kind of relative, right? If you're concerned about, you know, exactly how long did it take for this to happen, then we would go ahead and we would put time measurements on there. But these are usually relative pieces of information. We're trying to see what one of these signals does relative to another signal. Right. Another thing, make sure that if you put a picture in your lab that is not yours, put a reference in there right below the picture or above the picture saying where it's from. Okay. The 555 wiring diagram, there's one of those in the lab. You're fine to copy and paste that into your report, but put a note in there taken from Digital Logic Lab 5, right? And put the date on there. If you took it from a URL, put the URL in there. Just so that nobody thinks you're claiming that you drew this picture, okay? Because if you were to claim that, that's technically plagiarism. And when you write a report, you know, you take pictures and tables and words from other sources all the time. That's perfectly legitimate as long as you reference it, okay? You can take a whole class on how to reference things properly, but all I'm asking for is just something next to the picture saying, you know, taken from lab description, taken from engrcs.com, something to say that it's not yours. All right, and so one more time, here's the central goal of lab reports, okay? A lab report is supposed to be a complete presentation of what you've done so that somebody else could take your lab report and reproduce your work. So here's what I'd like you to do when you finish writing your lab report for Lab 6. Before you decide you're done with it, close your eyes, wait a few seconds, forget everything you know about Lab 6. Forget about traffic light intersections, forget about delay circuits, okay? Open your eyes and read your lab report and say, just reading this document that's in front of me, could I reproduce all the work that I did? Okay, if the answer is not yes, then there's stuff missing from your lab report. So experiment 1 on Lab 5, I saw things like, for Lab 5, I built a clock using a 555. Here's the waveform. And then, you know, there was this drawn on the page. If you don't know anything about Lab 5, is that enough information to reproduce what you did? Absolutely not. How did you hook up the 555? There were resistors, capacitors. Where did you put those? Where did you take the output? How did you power it? How much voltage? Where did you apply the voltage? Where did you apply ground? And then, was this observed? Was this calculated? Was this predicted? Right? So everything you need to reproduce the work that you did should be in your lab report. Okay? But this doesn't mean you have to write an essay. Okay? It doesn't mean you have to say, first, take a wire and plug one end into this hole, and then connect the other end to an alligator clip, okay? You can assume the person reading your report understands digital logic, understands Tinkercad, but they don't know what Lab 5 says. They don't know what Lab 6 says. So explain what you're doing in your lab report. Okay, that's what I'm really after in terms of a complete standalone report. So in that spirit, I posted a grading rubric for Lab 6. So Lab 6 has 2 experiments. First experiment, you're building a delay circuit. So I want to see 2 things in there at least. I want to see a discussion of experiment 1. Okay, tell me in your own words what it is you're doing here. Okay, I'm building a delay circuit. And then I want a wiring diagram. Now you can have more than this. You can have a block diagram. You can have a system diagram, but I want to see a wiring diagram, which means I want to see pin numbers on devices. To test your circuit, you're going to put a switch on the input and LED on the output. So I want to see the switch, I want to see the LED, I want to see power connections, all that kind of stuff. Okay, you're welcome to put in a Tinkercad picture, but that does not take the place of a wiring diagram. Okay, so 10 points for experiment 1. Experiment 2, discussion of experiment 2. It's a full traffic intersection with yellow light, okay, but tell me what that means. Pretend that I don't know anything about labs 1 through 5. I don't know anything about this course. What are you doing in experiment 2? Okay, just write. It doesn't have to be formal. Complete sentences, couple of sentences. Tell me what this experiment is about. Okay. System diagram, which will have 3 inputs, 9 outputs. Everything labeled, what's a 1, what's a 0, and make sure your labels are consistent with everything else you put in this experiment. Okay, that's 5 points. And then you're going to do some things before you actually design your circuit. Okay, you're going to use probably the approach we talked about Tuesday, where you have your old go signal, your green signal from a previous lab, you run it through your delay circuit, and then using the old green and the delayed green, you're going to look at that combination and decide what your lights should be doing. Okay, so you can sketch a block diagram for that, you can make truth tables, you can make timing diagrams, you might make K-maps and so on and so forth. You're going to come up with a set of equations. All of that stuff that goes into coming up with your circuit design, put that in your lab report. Okay, that's worth 10 points. And then a wiring diagram for your final circuit. This is the biggie. Okay, this is going to take a lot of work. This is 25 points out of 100 on your lab report. So a complete wiring diagram. This means it's going to have all the circuitry from your previous lab where you developed the green light signal for each of your 3 lanes. It's going to have a 5-5 timer with capacitors, resistors, all that sort of stuff. It's going to have 3 delay circuits, 1 for each lane. It's going to have logic on each of those for combining the old green and the delayed green to figure out red, yellow, and green lights. It's going to have LEDs, switches, and so on, part numbers, pin numbers, component ID block, and so on and so forth. And I reference a picture in page 62 of the text that shows you, the component ID block and logic symbols and things like that. Okay, I want to see all of these things in your wiring diagram. Really, really high quality. Okay, set it up in a way that makes it possible to read this. It's probably going to take more than 1 page, so here's what you can do. You've got your diagram, and here's an AND gate, and this is U7, and this was 1, 2, 3, and this has to go into the input of an inverter. And you're out of space. Draw a circle and label that, and then on another page put the same label and continue. That goes into an inverter, and this goes into an LED or whatever, right? And try to keep your lines horizontal and vertical. Okay, don't take this and squeeze it in down here into an inverter and run that through an LED and right? So organize it. Okay, you want this to be a wiring diagram so that somebody who you've never met before can just look at this diagram and they can build your circuit. Okay, and again, that's the question. If someone just looks at this diagram, can they build my circuit? So if you draw your circuit like this, right? Can someone reproduce your circuit from that? Probably not, you know. So imagine you're given this wiring diagram that you're putting in your lab report, and you're told, okay, you have to build this circuit. This is worth, you know, 25 points. Can you do that just by looking at what you've written? Okay, ignoring the fact that we can all read our own handwriting better than other people can. So try to make it, you know, legible. Try to make things so there's enough space to read, you know, the pin numbers and so on and so forth. Plan to spend a lot of time on it. Okay, so that's 25 points. Implementation in Tinkercad, 10 points. Conclusions, lessons learned, new experiment, another 10 points. That's 80 points. Okay, I'm putting an extra 20 points on here for what I call professional appearance. All right, so some of the lab reports I'm getting already are right where they need to be. They look like, you know, polished reports as opposed to drafts. Okay, I want everybody to try to turn in a report that looks like a finished report as opposed to a draft of a report. Okay, so what does this mean? You've got a single PDF file that contains, you know, all the information you need to reproduce the work, right? Is organized logically. Okay, within the report, there's, you know, an introduction with some sentences describing the report. There's experiment 1 with some sentences describing experiment 1, describing what you did, describing your observations, and so on. Things flow from one section to the next. Okay, everything should be labeled and referenced in the text. So if I'm drawing my circuit diagram, right, label this, you know, figure 1, and in the text say, you know, I built the circuit shown in figure 1, and then I tested the output X, right, and I looked at LED Q, and LED Q was on when input A was 0, right? So that it's really easy to connect what you're describing with what the person is seeing. All right. Make sure any material that's not your own is annotated as, you know, taken from some other source. Truth tables. Okay. Every column should have a heading neatly drawn. Rows should be horizontal, columns should be lined up vertically. Use a straight edge if you're doing these by hand. Okay, just get a ruler, get a thick piece of cardboard, something, so that it's really clear, you know, where a row is, where the ones and zeros are that belong to the same row, and so on. And, you know, somewhere preferably below the table, one sentence description, you know. Truth table for southern green signal. Okay, or whatever. And then in the text, you know, label that, you know, table 5 or whatever. In the text you can say in table 5 is, you know, the truth table that we got from the timing diagrams. Okay, wiring diagrams, as we keep talking about, right? Break your report into sections some way. I don't care how you do it, and I think everybody's doing this already, but, you know, something, you know, bold font or underline it or put some space around it or something like that. So it's easy to know, right now I'm looking at experiment 1. Oh, now I'm looking at experiment 2. Oh, now I'm reading the person's conclusions, right? Make your images clean, okay? Take a picture of it, cut and paste, right? Don't paste an image where I can see the side of the spiral, you know, wire on the notebook, or where you've torn it out, and so on and so forth. We have to draw out the whole 555 circuit in our wiring diagram. So technically, you know, you could paste a picture of that and then, you know, put a yes, it has to be in there somewhere. Okay. If you want to copy and paste it from the lab itself, right, you can do that, and you can paste that in and neatly connect the wires coming out of that to the rest of your circuit. But no, just a box with a 555 written on it does not let somebody else reproduce your work. Okay, because there's a zillion ways you can wire a 555. We're just using one particular way. So yeah, somewhere that has to be in there. But, you know, if you're careful about it, you can reproduce, you know, you can reuse the 555 as it's described in the lab assignment itself. All right. basically anything that can be typed should be typed. Labels, descriptions of figures, section headings, alt text, and so on. The things that you can draw by hand neatly are wiring diagrams, equations, K-maps, truth tables, timing diagrams, system diagrams, block diagrams. Those are the only ones I could think of. If there's something else that I missed that you think should be hand drawable, ask me. I'll let you know. But you know, this is a written report. It's supposed to look professional. It's supposed to stand on its own. Okay. So think about those things, and you know, if you want to send me an early draft of your report and say, you know, what do I need to change on this, I'll give you some feedback on it. Okay, preferably in office hours. And I want to basically get you like to where you're really set for Engineering 270, and then for other courses beyond that. So so if there's any questions about any of that, let me know.
Just curious about the Lab 5 experiment too.
Mm-hmm.
So I had it go from 0 to 9 and back to 0.
Okay.
And it stopped counting. Is that the end result that we should get, or was it supposed to keep counting over and over again?
It should keep counting, but as I said a while ago, it tends to hang up. The circuit that I showed in the beginning of class, you know, it does go back to 0 and continue counting seamlessly. But I've also had that circuit hang up on me. And it seems to be some sort of issue in Tinkercad.
I mean, when I had it like disconnected from the 7-segment display, like the counter itself, I tested it with the LEDs, it would count all the way up to 1111, and then reset, and then redo the count again. So I guess it is Tinkercad.
Well, no. So if it's counting up to 1111, you're not resetting it after 9, right? And that 7-segment display, if you ask it to display 10 through 15, it just shows you a blank. So for 12 seconds, it'll look like it's not doing anything, but it is. It's counting, but it's designed to display nothing if the input is greater than 9.
All right.
The issue with Tinkercad that people were having was that the simulation itself, you know, would show you simulated time about right here on the window. And that counter would actually slow down, and it would go about 1 millisecond per second. And that's where you know Tinkercad is struggling with something. But if you wired this up with QA, QB, QC, QD, and we wanted to roll over at 1010, so if you invert QA and QC and put all of those into an AND gate and send that to pins 2 and 3 on your counter, which are the reset inputs, that should immediately flip back to 0 when it hits 101010. So it'll count from 0 to 9 and then go back to 0.
I mean, I tried doing it through the AND gate also, but it also gave me the same end result, so I just left it out of the circuit.
Yeah, that's fine.
Also, there's like a kind of a pro to Tinkercad, mostly because if we had a circuit where some kind of counter, like how to say, overload and just burn through, in like the real lab, we probably wouldn't be able to figure that out until we took the entire circuit apart.
Right.
But Tinkercad kind of shows us where the problem lays.
It is nice that way, right? Because it shows you the little explosion symbol. And it's actually picking that up in cases where your circuit might still work correctly in the lab for a while, right? So if you have an input that's putting in too much current, over time that might cause your chip to fail. And Tinkercad will show you that right away. Yeah, totally. Tinkercad is useful if you're trying to be careful to not blow up the components. Or if you want to try to blow them up, it's also useful there too, because you never burn your fingers on it. All right, that was all I had for Lab 5 and Lab 6 comments. Again, Lab 5 looked really good overall. The main issues I saw that cost points in Lab 5 were You know, missing pieces like not having a timing diagram, not having a wiring diagram, and so on. But also, some of the circuits, the wiring diagram didn't look correct. For example, we needed to have pin 12 connected to pin 1 on the counter. And if you don't do that, it's not going to count all the way to 10, right? And I don't know if that was just an omission or what, but so double check your wiring diagrams as you're writing them up. Ideally, you're making a wiring diagram before you actually build the circuit, right? But the reality is, a lot of times people seem to build the circuit first and then make a wiring diagram, and that's more error prone because you can miss wires. All right. So, any other questions or comments? So someone says the template I gave you in the last Zoom meeting, is that the state machine analysis template? Oh, the green and delayed green thing? Yeah, timing diagram. Cool, good. Yeah, that's definitely a key to getting the yellow light to work. And be prepared for a big Tinkercad circuit, okay, for the yellow light. Everything that we talked about on Tuesday was really for one lane, so it gets replicated a total of 3 times, one for each lane. And each of the lanes kind of work independently, which is sort of cool. You know, they're tied together from your previous lab, which was deciding who got the green light. But the setup for the yellow light and the red is sort of independent from one lane to the next.
Just curious about lab 6.
Yeah.
So would we make it underneath a clock, or would we use a switch also in it to determine where a car would be there or not?
So you're going to have 3 switches, one for each lane, to simulate the car sensor. Okay, the clock is going to drive the timing of the yellow light. It's going to drive your delay circuit, basically. But ultimately, you're going to have 3 switches to simulate the 3 cars, and you're going to have 9 lights, red, green, yellow, times 3. And then the setup is, you know, set your switches so like there's no cars present, and then flip the switch that says there's a car to the east, and make sure east gets a green light, right? And then put a car on the south, take away from the east, and watch east turn yellow, and then red, and then south turns green, and that kind of thing. Then you want to play around with all the different combinations you can think of to make sure this is working correctly. And as I said, it's pretty satisfying when you see it work. The clock itself is just driving the delay circuit, right? I mean, this is a traffic intersection, so you've got 3 car sensors and 9 lights. How many inputs for this lab? So 3 inputs, which is the 3 car sensors, and 9 outputs. So yeah, your system diagram. Remember, the system diagram is the 40,000 foot view. So here's west, south, east. Car sensor, 1 equals car, 0 equals no car. And then, I don't know, green west, yellow west, red west. Green south, yellow south, red south, green east, yellow east, red east. Lights, 1 equals on, 0 equals off. Something like that would be your system diagram. But inside here is your 555, 6 JK flip-flops, and a whole bunch of AND gates and OR gates. Okay, all of that circuitry from your previous traffic control lab, plus your delay circuit from experiment 1, plus the logic you figure out while you're developing the circuit for experiment 2, All of that stuff is in here. But ultimately, it's just taking in 3 inputs and generating those 9 outputs. So your system diagram ignores all of those details. This is the outside world. And when you test your circuit, right, what you're doing is you're hooking up switch, 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 9 LEDs. Okay? But the wiring diagram for experiment 2 is going to show all of those details inside here, plus the switches and the LEDs. So that's where the 555 goes, and the capacitors and resistors, and a whole bunch of other stuff. Does that make sense? Cool. Yeah, you're welcome. All right, let's talk about Lab 7. We're going to spend the rest of the time talking about this. We're going to take a break in a minute, but Lab 7, you're going to need to use this student edition of software called the LDEC HDL software, and you're going to want to download this and install this on your own machine. So I put a link to the download in here. If you want, you can start that download and then play along. I'm going to download it myself and install it when we come back from a break. But basically, if you click through on that link, you'll get to a page like this. You want the free download, okay? So you click on that, you fill in your details. The email has to be accurate. I don't think everything else has to be. And click register, and within a few seconds, you should get an email with a download link, okay? I tried it just this morning. It worked really well for me, okay? And then click on that link in the email, and you'll get to a download page. It'll download a file. And I'm going to start with that file after a break and show you how to install it and show you how to use this. And then we'll talk about what it all means. If you do not have access to a Windows machine, please send me an email today and tell me that, okay? Because we'll have to figure out a solution to work around that, because this software only runs on Windows. If you have a Linux machine, it seems to run under Linux's window emulator, something called Wine. If you have a Mac, I think there used to be something there that you could use to run Windows software, but I don't know if it's standard or not. So, so if you don't have a Windows machine or something that'll run Windows software, send me an email today and let me know, okay? And we'll talk about options. So let's take a 5-minute break. Come back at 12:50, and the link will be in an email that you get after you say register. Okay, they'll send you an email, and it'll have a clickable link in it.